Welcome to this session one, dedicated to smarty materials and technologies. So we will have four presentations from our student, and we will begin by Ignacio Nilo Ruiz Riancho, who will speak about encapsulated rejuvenators for asphalt mixtures. The name of the project is Reducafalt. So this project has been done at the University of Nottingham, and at the moment, Nilo has joined ICOM Pavement Design and Asset Management team, always at the Nottingham office. So of course after his PhD. So Nilo, are you here? Are you ready to present?
Yeah, I'm ready. I'm gonna share my screen. So let me know if you can see.
I can see you, but I can't see your presentation for the moment.
1 second. 1 second.
I imagine. Okay.
What are you seeing now?
I see something, but I don't know if it's yours or not.
Yes, it is. I think so.
Okay, I think it's okay.
Yes, it's good.
Okay. Good. Okay. So, well, good afternoon, everyone. Thank you for attending to this meeting. It was a long time, so it's always nice to see you and have a presentation with you. So, yeah, well, you know that my name is Nilo Ruiz. My PhD was about the optimization of encapsulated oil properties to maximize asphalt self-healing. And my PhD was done at University of Nottingham under the supervision of Dr. Álvaro García. Okay, so as an introduction, it's important to remark the amount of money invested in the maintenance and the repairs and to repair the roads in the UK. And also it's important to remark the bad quality of the roads at least in the UK, and also the bad impression from the drivers, like the governments are investing year by year more and more money, but the drivers don't see an improvement in the quality of the roads. So that was the reason why we thought that the idea of the self-healing asphalt could be applied, because the concept of the self-healing asphalt basically provide a better recovery for the road quality. Also, it's automated, like it has a quick response in the early stage of the crack, so they prevent the potholes formation. And also, there are some environment-friendly bitumen rejuvenators that they can be used without a lot of impact in the environment. So the idea of the encapsulated bitumen rejuvenators is based on the addition of some encapsulated bitumen rejuvenators, in our case sunflower oil, inside of the asphalt mix. And when the cracks appear on the asphalt because of the traffic loads and the weather conditions, these capsules break. The capsules located in the most stressed area break and release the sunflower oil. And this sunflower oil reduces the viscosity of the bitumen, makes the bitumen go flow into the crack, closing the crack. So basically, the objectives of my PhD was to design and characterize the specific capsules to satisfy the mechanical requirements of the roads. To also optimize the capsule size and the strength to maximize the self-healing properties of the asphalt and enlarge the lifespan of the road, but without losing the mechanical properties. And also, we started with the development of a model able to simulate the mechanical behavior of the capsules. And and also we validate it with experimental test. And this was like the first steps for developing a design tool for the capsules, like it could be helpful in the future research. As a methodology, it's important to explain the process of the capsules manufacturing. It was based on an ionic externalization. So basically, we produced an emulsion based on sunflower oil, water, and sodium alginate, and we drop it in a calcium chloride solution where the chemical reaction takes place, and it's an exchange of ion exchange. And because of this ion exchange, we create the capsule, and the sunflower oil is encapsulated inside of a cell. Basically, we produced different type of capsules, modifying the diameter of the capsule and also the strength, just by modifying the amounts of sunflower oil or sodium alginate during the emulsion production. To characterize the capsules and analyze the influence of the diameter and also the diameter and the strength of the capsule, we characterize the capsules by thermal analysis, compression loss resist. We analyze the compression loss resistance. We did like EM imaging to analyze the porosity, the pore size of the capsules, and also see the influence of this in the self-healing. We had some computed tomography scans to assess the oil volume encapsulated, and also we can quantify the oil released by the capsules. So here you can see an example. This is an example of one of the capsules manufactured and one of the computed tomography scanning. So basically, the result we got, based on this result, we can quantify the amount of oil inside, the porosity, the size of the pore. Yeah, and we did this for the different capsules manufactured. So to analyze the influence of the capsules and how much we maximize the self-healing properties, we decided to use a wheel tracker in order to simulate the traffic loads, and we analyzed the fatigue resistance, the self-healing properties, just by seeing how many cycles of the wheel track were added after the addition of the capsules. We also analyzed the skid resistance and the routine, and the amount of oil released by FTIR spectroscopy after the application of the loads, and also the computer scanning tomography, as I saw before. Okay. Wait, I don't know. 1 second. Okay, yeah. So the first results we needed to get, it was the first question was like, are the capsules able to resist the compaction and the mixing process of the asphalt? So for that, we did a X-ray reconstruction of the asphalt after being compacted, and we got that we observed that some capsules were broken during this process, as you can see in this image. But this was just like around 2% of the capsules that you could see an obvious damage. Also, during the thermogravimetric study, we got this graph. Is presented there, that it represents the loss of the mass when the temperature is increased, and we can see that we have a loss of the mass for the asphalt mixing temperature, but also we need to consider that the capsules have some humidity, so we related this loss of mass to the evaporation the residual water evaporation. Okay, so this graph represents the another question was like we needed to find a compromise between the fatigue resistance and the healing index, because for some of the cases when the healing index was increased, the fatigue resistance was decreased slightly. So we needed to find a compromise where the reduction of the fatigue resistance wasn't too much, and at the end of the day we get longer life for the pavement. So basically we created this graph, and where you can see the healing index and the fatigue resistance index, and this green square are the capsules where we got an improvement in the life of the asphalt of more than 15%. So we actually, and this one in orange, we got an improvement, but it was lower than 15%. We just wanted to divide it like that. But none of the capsules gave us a bad result or and worse the lifespan of the asphalt. This graph represents the self-healing oil. I mean, the percentage of the healing oil release just before the resting period. So basically, it's the amount of oil released related to the healing index, and we can see that when in the samples where the healing index was higher, we also find a high amount of oil released, which makes sense. So it was something, but it was something to be confirmed. Also, another question was like during the PhD was like this oil released by the capsule is gonna cause rotting, and yeah, we can see this point here in one is the routing obtained for a sample of asphalt without capsules, and this one here you can see an increment of the routing after the addition of the capsules, but you can see that the increment, okay, you can see a trend, but the increment is not significant like for the road standards. 1.7 is something acceptable, so we consider that it's not a problem, the routing caused by the capsules. Here you can see in this slide an example of the how a capsule heal a crack, or yeah, basically it's like that. We have in the first photo in the preloading, this is a piece of asphalt, let's say, and here you can see the capsules, and the other white shapes here are air voids, and the black thing is asphalt. So after loading, we can see that the crack formation in this part, like air void, let's say. Also here, and after the healing, like it was 24 hours at environment temperature, 20 degrees. We can see that the capsule around the crack around the capsule disappeared. So yeah, that was the result of the computed tomography scanning. Regarding the model we developed, we decided to use a discrete multiphysics model. We basically we chose this model because we were trying to simulate a solid part and fluid part, what is a bit difficult to do it with FEM. So we decided to do it in a meshless program, discrete modeling. So basically, we designed the bonds and in any of the particles forming the cell, and we gave them some properties based on the physical laws. Yeah, and here we obtain this is the simulation we obtained. This one, the green line, we were trying different parameters in the modeling until we got the correct one, and we got that with the green line is the model with less density of particles, let's say. So we didn't get a good result, but we added also more density of particles in the simulation, and we
Nilo, be careful with the time. Huh?
Okay, yeah, I'm
okay,
finishing.
If you can conclude, sorry, but
yeah. So conclusions. Yeah, so regarding the conclusions, we got the capsules are able to maintain and even improve the asphalt fatigue resistance. For fixed size, weaker capsules may improve the healing ratio of asphalt, but they may also reduce the fatigue life. The self-healing results show the biggest capsules studied are effective because they could be compressed by the aggregates, and asphalts with higher self-healing show increased routing, which may be related to the amount of healing agent released. So thank you very much for your attention. Yeah, if you have any question now or later or whenever, you can ask me.
Thank you very much, Ignacio, Nilo. So we will wait after all the presentation for the question on the discussion. So stay here with us.
Yeah, no problem.
Okay. Thank you very much. So now it's time to welcome Paulina Leiva Padilla. Paulina, you are here?
Yes, hi.
Hi, Paulina. So Paulina will present us a work about mechanomutable asphalt binders for the construction of smart pavement. So this work has been done at the University of Granada in the Laboratory of Construction Engineering. And at the moment, Paulina is a postdoctoral researcher at University Gustave Eiffel, and she's working on the effect of truck platooning over the pavement structures and the implementation of new pavement instrumentation strategies. So Paulina, we are hearing you.
Okay, thanks so much, Emmanuel, for this kind presentation. Can you see my screen now?
Yes, yes, good.
Okay, thanks so much. Okay, good afternoon or good morning, everybody, wherever you are. So yes, as Emmanuel told you all, my project was called Mechanomutable Asphalt Materials for the Construction of Smart Pavements. And in this project, I work at the University of Granada with the supervision of Professors Mike Rubio and Fernando Moreno. And to start with this presentation, I would like to do this kind of introduction of what are the generations related with the pavements along the story. So as we can see, the roads have evolved from the Roman and rustic roads that were after paved, extended to high capacity roads. And in the last decades, and well, all of our smart TTNM projects are related to the sustainable and the smart roads. So as most of our projects were trying to focus on, we were looking at these future needs that the road has. That, for example, are more durable roads that are cheaper and that requires less maintenance treatments or even cheaper treatments, that are capable to communicate with others, to manage the traffic and their own performance under service, be energetically self-sufficient, help with the traffic of the autonomous vehicles, and improve the road safety. So one of the strategies to manage or to try to cope with these needs is, well, the production of new materials, a new kind of smart materials that are trying to reproduce or represent these abilities that have the living beings, the human beings, this capacity to self-recover, as Nilo has already explained before, materials that are capable to emit or receive signals or messages that can communicate with the different elements in the road, sensitive materials, materials producers and savers of energy, materials capable to assist the guidance of vehicles, and materials used for road safety. So the mechanomutable smart materials are inside this classification of materials, and the concept of mechanomutable was born there at the University of Granada because it was the first usage that was studied there. Well, there is a composed word which has the prefix mechano, which is linked to the concepts involving the mechanics or mechanisms, and mutable, subject to change. So it's this capacity to change the mechanical properties of our asphalt materials by the use specifically of magnetic fields. So with that, what we did was take our conventional asphalt materials composed by aggregates and asphalt binders, and we modify them by the use of materials with electric and magnetic properties. So these materials could have an extra physical domain, which is the electromagnetic domain, which make them capable to be perceived by magnetic field sensors or to react to permanent magnets, induction coils, electromagnets, and so on. So this concept of mechanomutable asphalt materials was evolving, and we are not just having these mechanical changes. We also can have these magnetic changes and thermal changes. So are more than mechanomutable, are now magnetic or thermomutable materials. So during this project, we were studying these three pillars associated to this type of effects that we can produce with these materials. So the main objective was evaluate at the mortar scale and in laboratory the mechanomutable asphalt materials for the usage in the construction of smart pavements. For this purpose, and well, as already David explained before, we were trying to support the usage of materials that can be recycled or reused, more sustainable practices. That is the reason why we use steel fibers from the end-of-life vehicle tires. And we, as we know, these particles can be kind of dangerous for the vehicle, so we try to propose the use of a kind of smart layer as an intermediate layer in the surface, the layers of our pavement. So like with these two purposes, first of all, protect the tires of the vehicles, and the second one that can also work as a kind of anti-reflective cracking system. So our thin layers from 10 to 20 millimeters with high content of binder and also small particle sizes. So as this presentation should be short, I'm not going to talk about the first and the third pillar, and not just about the second one, which is this capacity to emit magnetic field signals. So the principle is kind of giving a kind of language to our pavement and give to the vehicles the capacity to understand this code that we are assigning to the road. So basically what we are doing is codify the road depending on the usage that we are trying to give to the different regions in the road, and give to the vehicle the capacity to understand our road. It's like kind of a translator to understand this code that we are given to our road. So as well, this is just the beginning of the study of this capacity. There are not specific tests for this. And that is why we propose this device that you are seeing on the screen that actually helped us to characterize different parameters, as for example, the height of where we are placing the magnetic field sensor, the distance at which the vehicle is approaching, or also this speed at which the vehicle is approaching, and the amount of magnetic material that we are using in the sample. We evaluated this in the laboratory, and after that, with the results we got there, we tried to adapt an application in real life by using a scooter. So here, I'm just going to show these results here because of the time, but well, we explore in laboratory these parameters, and as you can see here, there is certain combination of these parameters in which we can manage or we can program the way that our vehicles are understanding the different messages that our pavement can give to them. So this is the second part in which we try to prove this concept, trying to adapt this experiment that we did on laboratory by producing this element that we install in our scooter, and also these plates with specific amounts of magnetic materials. And as you can see here in this video, actually we achieve that this scooter could slowly stop when it's passing through this region with a high intensity of magnetic field. And also it's not only to send this message to the scooter, you can also have the message in other elements, as for example, the smartphone that you are seeing on the video and with the message there. So in conclusion, what we can say from this project is that, well, it was possible to explore the use of mechanomutable asphalt materials for these three applications that I already explained at the beginning: improving the mechanical properties of the surface layer of the pavements, codify our pavement to use them as a tool in the autonomous vehicle industry, and help in the definition of rehabilitation and maintenance strategies for payments. And for these two last applications, well, the first one and the last one, I invite you all to read the documents that we produced to have a little bit more detail about it. And that was my presentation, and thanks so much.
Thank you, Paulina. Very dynamic presentation. Thank you very much. So, as I said to Nilo, remain here in the room for the question at the end of the session.
Thanks so much, Emmanuel.
Thanks. So now we are welcome Gaspare. Gaspare, are you here?
Yep. Hello, hello. Good morning, everyone. I'm Manuel.
Hi.
Can you hear me?
Yes. Yes. We could hear you. So the name of your project is Computational Design and Rheological Characterization of Complex Emerging Materials. This work has been done at University of Palermo, and currently you are working at the University of Palermo as a research fellow, so working on the project Rubber Wrap that aim to provide scientific evidence regarding the feasibility of effectively multi-recycling rubberized reclaimed asphalt at laboratory scale and beyond. So Gaspare, up to you.
Yep.
Could you share your screen?
Yes. 1 second. Okay, can you see?
Yes, good.
Hello everyone. Happy to see you again. So my name is Gaspare Giancontieri, and I've been working within the SMARTY project in the project called Computational Design and Rheological Characterization of Complex Emerging Materials. My supervisor was Davide Lopresti. So let's talk about my project. So first of all, what is a complex materials? Nowadays, engineers are continuously developing performance-enhanced material to maximize the durability and recyclability, but also carrying out to minimize the environmental and economic impact of the final product. In this research, complex materials were defined as a mixture in which two or more phases coexist together, exhibiting a deviation from the simple Newtonian behavior and characterized by unusual mechanical response to applied stress or strain to the variety of those structures. Complex materials are widely used in many applications, such as pharmaceutical, food industry, cosmetics, but here the focus is on engineering application, especially pavement engineering application. Materials such as heterogeneous bituminous binder, bitumen emulsion, biobinders, and bituminous cement mixture are considered complex. So, although it has been proved that they are more sustainable than conventional ones, their use is still limited due to a lack of engineering properties needed to characterize them. For example, when we deal with modified bitumen, such as heterogeneous bituminous binder, one of the key parameters for the characterization of this class of material is the dynamic viscosity. The dynamic viscosity is really important, for example, to define the equiviscous temperature for design purpose, to guarantee the adequate coating of the aggregate, for the material classification, but also during product development. This exercise to define the the dynamic viscosity is usually carried out in laboratory by using rotational viscometer. However, due to the high level of heterogeneity, carrying out rheological measurement on this kind of material using standard equipment it might be challenging. Indeed, phenomena such as separation, sedimentation, and agglomeration may occur within a measuring chamber, making the results not representative of the original sample. Also, laboratory tests are costly and highly resources consuming. Therefore, an innovative approach to characterize the engineering properties of complex materials is needed. The main objective of this research was to promote the use of emerging materials, emerging complex materials for more sustainable civil engineering application by using a laboratory and computational approach. This approach was used to optimize the currently available procedure tests that have not been designed for complex material, but also identify engineered properties to characterize the rheological behavior of those materials. In the first part of the research, the idea was to provide a deeper understanding of the before-mentioned phenomena, such as phase separation, sedimentation, agglomeration, by using a computational fluid dynamics model to simulate the laboratory test and use an innovative visual aids to monitor the sample stability of heterogeneous bituminous binders during rotational tests. The numerical analysis was also complemented by a laboratory campaign to provide further details about the sample stability phenomena during viscosity measurements of heterogeneous bituminous binder by comparing a conventional standard testing setup, such as the standard spindle 27, and a dual helical ribbon previously developed during my PhD study. Here we can see a picture of that shows the viscosity reading of heterogeneous bituminous binder at two different temperatures using a standard cup and bob spindle. According to the standard, the first 15 minutes the viscometer motor was off in order to allow the sample to reach the thermal equilibrium. After 15 minutes, the motor was turned on, and it's possible to observe that after an initial high value, the viscosity tends to decrease. The same scenario happens when the temperature is high. But let's see what happens when we use a different shape, such as the dual helical ribbon. A stable trend is recorded from the beginning at both the temperature compared to the conventional impeller. This means that the sample might be suffering sample instability phenomena. From these results, it arises the question if we are correctly measuring the rotational viscosity, for example, of rubberized bituminous binder. To provide a further insight, parallel to the experimental campaign, a numerical model was reproducing the laboratory test was developed. The numerical campaign indeed helped to identify that the SC27, due to its geometry, create low velocity field at the top and the bottom of the tube, as you can see from the simulation, while all the stresses are distributed around the vertical wall of the spindle. The DHR instead allow a better distribution of the velocity field, or the velocity flow field, thanks to the axial pumping, where the inner blades push the fluid upwards, while the outer push the fluid downwards, allowing a continuous recirculation on the fluid flow. The particle distribution investigation showed that using the standard spindle, the rubber tends to settle down to the bottom of the sample due to the gravity, and making the result non-representative, using the DHR that allow to test a well-distributed sample, and this theory contribute in guarantee a stable trend of results observed during the experimental campaign. Finally, in a further investigation, the adoption of dual helical ribbon is proposed for real-time monitoring of crumb rubber modified binders during manufacturing and hot storage. The aim of this research was to evaluate several crumb rubber binders with different crumb rubber modified type and content. binder have been manufactured and tested at different storage temperature to show the capability of this procedure. Here we can see that the real-time monitoring of each blend can be translated in 5 parameters that allow performing a comparative analysis of the modification process during manufacturing and of storage. Finally, I would like to say that this research is currently further developed by using a dynamic share rheometer in place of a rotational viscometer in a new project, Rheomix, that is developed in collaboration with Anton Paar. Many thanks. Thank you.
Thanks a lot, Gaspare.
Thank you, Manuel.
Thanks for your very precise presentation and concise presentation. So,
Thank you.
So we are going to see a video from Domenico Vizzari, a video about the development of a pavement system able to capture solar energy. So Domenico can't be here because he is in a plane due to a COVID reason. He can be here. So I will try to share my screen in order to watch the video. So can you see the video?
Yes, Emmanuel.
Okay.
Yes.
So I will run the video. If something goes wrong, don't hesitate. I will stop and we begin.
Manuel, we can't hear anything. I think you have to share the sound as well. I don't know. It's an option in the sharing.
Exactly.
Yeah. Device.
It's an option. So
yes, it's an option. You have to tick a box or something like that.
I'll suggest, Emmanuel, you stop to share, and then you share it again. And when you share it, there will be this option at the top. You have next to. So, stop sharing again. When you share it, next to share content, you have include computer sound. Sorry, we didn't rehearse that. So you share it, and in the Microsoft Teams
It's a tick
window
in the upper part that says include the audio system.
Include
computer sound.
Good.
Perfect. Okay, now it should work.
Let's go.
Good morning. My name is Domenico Vizzari, and today I'm going to talk to you about the project development of a payment system able to capture solar energy. But before to introduce you the project, I would like to ask you, why harvest energy using the rod payments? Well, first of all, because of the possibility to exploit existing surfaces to harvest energy. At present, there are two main energy sources, the solar radiation and the traffic load. The solar radiation can be directly converted into electricity thanks to photovoltaic cells embedded in the semi-transparent layer. An alternative solution is the heat exchanger. It consists of pipe embedded into the asphalt. During summer, because of the high temperature of the pavement, the water which flows into the pipes is able to extract heat energy. The third solution is the piezoelectric rod. It consists of piezoelectric material embedded into the pavement, which is able to generate electricity thanks to the passage of the vehicle. Our idea is to merge together a photovoltaic rod and an heat exchanger. Our prototype is a multi-layer pavement composed of a semi-transparent layer made of glass aggregates bonded together using polyurethane, an electrical layer containing the solar cells, a porous concrete layer for the circulation of the water, and a base waterproof layer. The potential use of the photovoltaic of the hybrid rod is the generation of electricity thanks to the photovoltaic cells, the ability to contrast the heat island effect using water as a heat exchanger fluid, the possibility to exploit the harvested energy in the porous layer by means of a heat pump, and to stock the water during summer and reuse it during winter as de-icing. Now I would like to talk to you about some results regarding the harvested energy. Here I'm going to show you the experimental setup that we built in our laboratory. We have a lamp which is able to simulate the sunlight radiation, a mold where we placed our prototype, and a pump which makes flow the water into the prototype.
Manuel,
Yes.
unfortunately, we can't see the slides.
For this test, we compared
Now I think we can.
Prototype, and we performed a test with a sinusoidal signal of the lamp because we wanted to simulate the change of the light between day and night, and a square signal. We used the sinusoidal signal to evaluate the harvested energy, while we used the square signal to evaluate the power loss of the solar cells. Now I'm going to show you the results regarding the... As I told you before, we compared the two generations of prototype. In the first generation, we had a porous asphalt as a porous medium, which had a porosity of 20%, while in the second generation, we used porous concrete with porosity of 34%. In this figure, we have in the horizontal axis the time, in the first vertical axis the harvested energy, and in the second vertical axis the power lamp. The orange line represents the harvested energy of the first generation prototype, while the blue line represents the harvested energy of the second generation prototype. It's interesting to observe how, on average, the second generation is able to generate is able to stock almost 2 times more energy than the first one. We also performed a cost-benefit analysis based on 3 different scenarios: in situ application of the prototype, prefabricated slab based on the concept of removable urban roads, and rectangular prefabricated slab having rectangular shape. As you can see in this figure, we evaluated the cost of the prototype during 20 years for the 3 different scenarios. And we compared these results with the benefits that we can obtain from the prototype. As you can see, after 8 years, the prototype could be rentable. In conclusion, the hybrid rod has the potential to provide sustainable energy, enable decentralized expansion of renewable energy source, and avoid to occupy new lands. The harvested energy can provide heat to the nearby buildings, alleviate road heights, and mitigate the urban heat island effect. Despite the high cost, in long term, the hybrid road could be profitable. Next step will be the identification of certain areas where the use of existing surface could be advantageous, the construction of a full-scale prototype, which is already done, and the validation in an operational environment. And finally, to assess the life cycle assessment of the hybrid road. Thank you.
Okay, so I will stop to share. Okay, so Domenico is not here, but I can answer to the question about pavement energy harvesting since I'm in this project. So now we have some time for question. We have more or less 6 minutes for question.
Okay.
So perhaps I can begin with some question to Nilo. So
Yes.
Nilo, I would like to know if your system has been patented.
Well, to be honest, I don't know. Like, I didn't do the patent, so, but I don't know if Alvaro did it with further research. I know that there are more projects going on, like with larger scale. They are actually they had some sections in some quarries already with the capsules. They are testing on site, and probably they are gonna come other sections in bigger roads, but that is what I know. Yeah, I didn't write any patent or during my research.
And do you know if some companies are interested in this type of application?
I don't know. No companies. No company didn't contacted me. So what I know, I think. Well, I don't know. I don't know if I can say which companies are in the projects they are going on. So, but I know that there are companies.
So who can say?
Maybe my supervisor. I mean, it was a long time. I'm not there working in the office, so I don't know how it's going.
Maybe I can add something, Manuel. That's Davide. From what I know, the technology has been actually upscaled and validated with some sections, and this was with an interest of the main road authority in the UK and also with the main asphalt contractor. So it is actually going forward.
Yeah, I know that they developed a machine to manufacture these capsules in a large, faster, more amount. But basically, the capsules are the ones I developed in my PhD. The same structure, the same internal structure, porosity, amount of oil, all of that. Yeah.
I think Simon has a question.
Yes, I have two questions, in fact, for Nilo as well. The first one is, do you have any idea of the size of the crack needed to break the capsules? Is that micro or micro cracks?
The capsule the capsules don't break because of the crack. Sometimes break, sometimes they don't break. It depends on the pressure the capsules receive or the loads. So sometimes the capsule just release the sunflower oil like a sponge. Like they receive the load and they release the sunflower oil. So it's not like no size is. I mean, the crack is not releasing. It's not releasing the sunflower oil. It's the load received by the road. Yeah.
So you can have some oil in the material without having any.
Not really, because we need
defects
like
or, yeah.
we need a space. So we need a crack to allow the sunflower oil going out of from the capsule. But sometimes this capsule, this crack is too big, and the effect of the sunflower oil is not gonna do anything. But for shorter cracks, is effective. Yeah.
And my second question, but maybe we won't have time for other questions, but we have. Okay, so the second question was about the industrial use of this kind of products. Do you have any idea on how to use this product on a plant, for example, an asphalt plant?
I mean, we didn't do it. Well, actually, we went once to try it in an asphalt plant, and they tried it, and there were any problem in the manufacturing or mixing process. And also now, as I said before, they already built a real section in some quarries, and they didn't notice any problem with the resistance of the capsules in the manufacturing or the mixing or the temperature resistance. So far they are working well even in real life. I mean, I demonstrated that in the lab. They are working okay. We are getting like more than 50% of more life, but in real life, so far they are going okay. But we need more time to see the final results, because it takes more time in larger scale. So.
Okay, thanks a lot. We have another question from Safer Aider.
Okay.
Hello.
Yes.
Yeah, go.
Now, you listening?
Yes. Speak slowly on the louder.
Sir,
we can hear.
Sir, my question is in computational design and characterization of rheological complex emerging materials in this presentation, that researchers has used crumb rubber modified asphalt. It is mentioned in standard that we cannot use modifier having size greater than 0.25 micrometer or 250 micrometer. But in research, it has been used that crumb rubber has size more than 250 micrometer. So how the size of crumb rubber modified the properties of asphalt binder?
Gaspare, could you answer?
Yeah. So it was for me, not for Nilo, right?
No, it was for you.
Yeah, I guess not for me.
So can you please repeat it, because I didn't understand exactly. You said that we cannot use rubber bigger than.
It is question that it is mentioned in the standard DSR standard that we cannot use modifier having size greater than 250 micron. But in your research studies, I have also studied different research articles in which the crumb rubber modifies crumb rubber having size greater than 250 micrometer. So, however, it is mentioned in standard that we cannot use, but why researchers are using size greater than 250?
Okay, in this case study, we are not talking about parallel and plate configuration, right? We are talking about rotational testing. So it's a different setup. We are testing modified binder under the rotational testing setup. So we go higher. That we are actually testing modified binder already produced. Although we can even produce the binder with this technology, but we are talking about rotational testing.
Okay. On this modified binder, you have not performed DSR testing.
We also perform the rheological characterization of the material, but it was just to provide information about the materials. This study aims to investigate the sample stability phenomena that might occur during rotational testing, but also might occur during at plant scale, during plant scale study.
If I can quickly add something, Manuel.
Sorry.
Can I add something quick just to support what Gasper said? Safir, what you may refer is what Gasper said, DSRs in terms of plate geometry. And there could be a problem with the film thickness. But in our case, we are trying to find a way to test binder modified with big, let's call it, particles that may come also by the rubber swelling. So it's not necessarily that you actually have rubber of a certain size. During the swelling, it may get bigger. So with this type of rotational measurement, we can do dynamic mechanical analysis. We can't because it's a rotational test, but we are able to assess viscosity, at least, with a more accurate approach. And that is what we actually realize, simply because we don't have phase separation during the testing. So I would suggest to go and read what Gasper did in his research, maybe publication, and possibly is going to shed some light.
Right, sir. Thank you so much.
Okay, thank you very much. I have a last question for Paulina. Paulina, you are here? You are still here? So,
yes.
Paulina, it seems that the mechanomutable asphalt binders could have lots of application. From your side, what is the most promising application of this type of technology?
I guess, well, one of the most explored, and I can say one of the most used right now is the third application, in which you are using this coils to try to increase the temperature of the pavement to try to heal the cracks. So in this field, there are also field tests, and there are certain applications that are already now implemented. But I'm saying that it was one of the things that have already have certain advances in real applications. But the rest are also something that could be promising to explore. So for me, it depends on, but one of the ones that had been more explored is this one, the one related with the usage for kind of rehabilitation strategies. Yes, I don't know if that replied to your question.
Oh, yes, of course. If, for example, you continue your career of researcher at University Gustave Eiffel, do you want to implement this type of technology in?
Well, it can be, yes, because if there is a possibility also to interact or to do a kind of collaboration, it could be really good also because, well, we still, and I know that is kind of a really good bonding between the University of Granada and University Gustave Eiffel. So it could be really good actually to try to test or to try to do something else about what we can do the next step in one of the applications, or why not in more than in one of the applications that we have for this.
I imagine that lots of cities can be interested, especially for the scooters.
Yes, well, actually, that was the proof of concept. But also to achieve this implementation, complete implementation, we need to study a little bit more to see, because depends on the type of sensor that you are using, depends on also the environment that you have around the road. So there are different variables that should be adjusted, yes, for this application. But yes, for sure.
Okay, thank you very much, Paulina.
Okay. Okay.
Thank you, Ignacio. Thank you, Paulina. Thank you, Gaspare. And Domenico also, even if he is in a plane. So, Davide.
Thank you, Emmanuel. I think we'll have a dessert break.
Yes.
and come back at 45, if I'm not wrong. Let me see.
7 minutes.
No, it's at 40. So 7 minutes, maybe. Yes, Simon, it's going to be a short break. It's going to see 2:40. Thank you, Emmanuel. See you later.